So we will be moving forward with the next presentation, which is Michael Lombardi. Can I get a round of applause, please?
So I speak into this. The forward arrow. Okay.
And flag you down. You have 5 minutes.
Okay. Good morning. So I have the, I guess the mixed blessing of following the Grape 2 talk with John Gibbons, who also designed Grape 1. But to, I guess to paraphrase Shakespeare, I come to praise Grape 1 and not to bury it. This is a picture of the setup in my ham shack in Broomfield, Colorado. So you've all seen this before, but Grape 1 is this is Grape 1. The WWV VH receiver is a small board on the left. It's attached to the Leo Bodner mini GPS-DO. You can select the frequency of 2.5, 5, or 10 megahertz with the jumper, and there's a Raspberry Pi computer that controls everything. In my setup, I just hang the GPS-DO antenna in the window. In my antenna, and we'll show some data, I'm using either a 60-foot piece of wire indoors or an end-fed half-wave antenna in the trees in my backyard, which is what I use for ham radio, with a 9-to-1 unit. And I ran that for a few days. So what I'm going to talk about is not space weather, because I don't really know a lot about space weather. And I know that's what the Grape 1 was designed for. But I'm going to talk about recovering or measuring WWV frequency with the Grape 1. So the primary function of V and VH is to serve as a frequency and time interval reference. And it's one of the oldest services operated by the federal government. WWV has been broadcasting standard frequency since 1923. And this instrument shows us some stuff I had not seen before. The Grape 1 measures the Doppler frequency of the received signal by comparing that to a GPS-DO. And it's really neat because you have atomic clock accuracy at both ends of the radio path. You have the GPS atomic clocks falling out of the sky, and you have WWV, which is referenced to UTC-NIST, which is the national standard for frequency. And it records data every second in units of hertz with a resolution of 1 millihertz. And just for a little bit of background, you determine frequency offset or accuracy with the basic equation delta F over F, where delta F is F measured minus F nominal, and F is F nominal. So if you have a 1 millihertz offset with the 2.5 megahertz carrier, your unitless frequency offset is 4 times 10 to the minus 10. 1 millihertz at 5 megahertz is 2 times 10 to the minus 10, and 1 millihertz at 10 megahertz is 1 times 10 to the minus 10. And like a frequency counter, you can get more resolution if you average for a longer interval. So historically, and this slide's pretty busy and I don't need to go into all this, but historically WWV has been used to measure frequency usually with a beat frequency method where you actually listen to a beat note. If there was a big enough delta F, you could actually hear the beat note. And I remember in the early days people listening for the beat note with headphones, where they would inject a frequency into the receiver. You can use oscilloscope methods. You know, most of you know about the FMTs, the ARRL frequency measurement test, where you have 1 minute to determine the frequency of an unknown carrier. And there's articles about that. And normally, the receiver's calibrated at test points against WWV, and then you do some kind of interpolation to get to the unknown carrier and assign some kind of offset. And now you have the modern software like FLDigi or WSJTX, where you can do this. But all of these things tend to be similar in the sense that they do a quick check or an instantaneous check of the frequency using WWV with a short measurement and they tend to be limited to a few hertz, for example, or maybe a tenth of a hertz. So maybe you can get frequency accuracy down to about a part 10 to the eighth. So I only know of one long-term measurement that was ever really published. There might be others, but this was in 1974, a long time ago, almost 50 years ago, where Nobu Hironaka, who was Dean Okiyama's predecessor at WWVH, did a measurement from 5,500 kilometers away of WWV, because that's the distance between V and VH, where he wrote down, he did a time of flight measurement, and he wrote down the time that the WWV signal arrived in Hawaii every day at about 1915 UTC, and then he did a 5-day rolling average, and you can see in that red circle the numbers that he got in microseconds. And 10 microseconds a day happens to be a part 10 to the 10th, because that's a measurement in the time domain, but delta t over t in the time domain is equivalent to delta f over f in the frequency domain. So he did a frequency measurement of parts 10 to the 10th. But it was, albeit a very difficult measurement, it took a long time, but he was able to do that and publish it. So what Grape1 does, Grape1 lets you do something like that much faster. You have continuous frequency data. And what I'm going to talk about for the rest of the presentation is using Grape1 data to compute the Allan deviation. So the Allan deviation is well known in time and frequency metrology, but probably not so known to all of you. So I just want to introduce it briefly. It's a metric that serves as the industry standard for specifying the frequency stability of an oscillator. And it's written up in the IEEE standards documents and so forth. It was named after a fellow named Dave Allen who worked at NIST. And he first published this a long time ago in 1966. But it's evolved since then with many, many variations and modifications and lots of software and so forth. The mathematical notation for ADEV is sigma y of tau. So sigma is the same sigma you know about with standard deviation. Y is frequency. Tau is the sampling or the averaging interval. And the one thing to know about ADEV, the most important thing, is it's not a metric for measuring frequency accuracy, only for stability. So it doesn't tell you whether the frequency is right or wrong, it only tells you whether the frequency stays the same. But when you're looking at something like WWV or GPS, both things have inherent accuracy. So what ADEV does for you is it shows you the limit of the accuracy you can obtain, because the accuracy cannot be better than the stability. So that's what its main virtue in this type of work. So in the interest of time, I'm not going to talk about the equations for ADEV, but I am going to just provide some links, and if these slides are available, you can use these for reference, about where you can get a nice reference book that describes these statistics, and also where you can get software. In the most famous program to compute Allan deviation was written by Ham, Bill Riley, who came out of the GPS program. And he put his program called Stable 32 in the public domain after he retired. And so I have the links here. And there's also Python libraries where you can, for Allan deviation. So Allan deviation plots are log plots. They show unitless frequency stability on the y-axis and the averaging or sampling interval on the x-axis. And from the slope of the line, you can determine the noise type. And normally, the frequency stability will improve until it reaches the flicker frequency region, and then it will start to random walk off frequency. But if you were measuring an oscillator, that flicker frequency region is normally where you stop the measurement, because you won't gain anything else by averaging for a longer interval. But with WWV, which is inherently accurate, which is being corrected, its frequency is being corrected to agree with coordinated universal time, you don't really reach a true noise floor. So this is an FL-Digi graph obtained from the Grape-1 of the 5 megahertz Doppler shift recorded at the ham station W0 DAS in Fort Collins. Dave Schwartz. Dave was only 15 kilometers from the station. He has a quarter wave vertical, and you can see it's just a flat line. So this Doppler shift frequency is only fluctuating by a few millihertz. And if we run the Allan deviation on that, it looks like this, where the path stability reaches about 0.2 parts per billion, or 2 times 10 to the minus 10 after 1 day of averaging. So this is showing me I can recover frequency from WWV of 2 parts in 10 to the 10th, which is, you know, I had not seen a graph like this before. So I got the Grape-1 from Dave Schwartz. I took it to my home, my QTH in Broomfield. I'm 81 kilometers from the station. And here's a 5 megahertz Doppler shift plot. Just to review, the black line is the Doppler shift frequency, the red line is the power. And it's a little bit noisier. I ran for, I believe, 24 days. This is just 1 day. And the Allan deviation looks like this, where after about 1 day, I get down to about 2 parts per billion. But you see this sharp drop off. There's a sharp improvement after 1 day of averaging, about a 4 times improvement. And that's a characteristic of the Allan deviation, because you need to average long enough to remove the diurnal effect. So we have the diurnal effect of sunrise and sunset. And you can see the low points on that ADEV curve are all the even multiples of 1 day. So I did the same thing with my outdoor antenna. It gets very clean at the end of the graph during the daytime after sunrise, where the 2.5 megahertz signal, the ground wave is very, very flat. It's almost similar to the Dave Schwartz data, but the nighttime is not so good. And the Allan deviation, going out to about 3 hours, gets down to below 1 part in 10 to the 8th. And then I did a very long run of the 2.5, about a 30-day run, and it almost looks exactly like the 5 megahertz, where I get down to about 2 parts in 10 to the 9 when I average for 1 day. So finally, one of the questions that's come up is, does the Leo Bodner GPS-DO add any measurement uncertainty to this type of measurement? And one of the things I do at NIST is I calibrate GPS-DOs. We do them for customers. And I would have to say that the Bodner is probably one of the least, it's certainly the smallest and one of the least expensive GPS-DOs, but certainly not one of the most stable. But even so, it reaches a frequency stability of about 1 times 10 to the minus 12 at 1 day. So most GPS-DOs are about an order of magnitude better than that. Some even reach, low to mid parts and 10 to the 14th. So the Bodners are right around 1e to the 12. But that's it at 1 second averaging with the 15 kilometer baseline ground wave data. At 1 second averaging, the Bodner is about 20 times more stable than the WWV ground wave, and about 200 times more stable at 1 day. So I would conclude it contributes no discernible measurement uncertainty at all. So to summarize, I think, for the Grape-1 is a very powerful instrument, and it provides more comprehensive frequency measurement data than I had seen in all the years I worked for NBS and NIST. I think perhaps using ADEV can help validate the Grape-1 and later the Grape-2 measurements. With better antennas and more carefully monitored conditions, certainly could do better than I did for my home QTH. And I think space weather research could potentially benefit from the use of the Allan Deviation because it's a well-known metric. It's pretty simple, and I think it could be helpful. And I'd like to thank the following people, some of whom are here, but especially also the radio station staffs at WWV and WWVH who are not here. And finally, I've included in the slide deck some reference slides about how to use Stable 32 in case anyone's interested in running the FLDigi data and computing the Allan Deviation. Thank you for your attention. I guess we have time for a question or two if anyone has one. Oh, here comes the mic.
Oh, thank you. Mike, do you have a systematic way of telling a consumer of your data that the background signal was non-stationary? Like that you had a diurnal variation in the stability of your signal reception?
A systematic way? Well, you notice like in that long-term measurement I showed from 1974, you made the measurement at the same time each day. And if you did that, like say I even did that from my station and I only measured the 2.5 megahertz at 2 in the afternoon or something, I'd get some really good results. But obviously, GPS has a diurnal too, due to the ionosphere, but it's a few nanoseconds. In WWV, it's very large, the skywave, ground wave separation, and if you average for 24 hours, you're going to cancel it somewhat, but you would do better, obviously, looking just at the ground wave. And obviously, you can't do that unless you're very close to the transmitter. Any other questions? Okay, thank you.